Our next speaker, Kevin Hennessey, is a principal research scientist at CSIRO and is recognised as a national authority on a range of climate change issues. Kevin Hennessey. This chap coming.
Just while I'm being mic'd up, if you can hear me from the back, by way of introduction, I've been with CSIRO for about 18 years. Started with a very small group who was called the Climate Impact Group. Since then, that's grown from a couple of people to about 15 people today. We currently do research on past trends in climate variability, both locally and globally. And we also do some work on projecting regional climate change into the future. The talk today will effectively be just looking at a bit of information on the climate change science within the context of what the Skeptics are doing. While this is being loaded, the structure of the talk will effectively start with a bit of background about the scientific method, which is the underpinning theory behind establishing scientific fact from scientific theory. And effectively what that is we use, it's an evidence-based set of assumptions where we look at all of the data and the theories available. They're tested. It involves the consultation with skeptics, of course, to try and disprove theories. And it's only the theories that withstand those tests that actually go on to be accepted theories. Okay, so as I said, I'll start with the scientific method. I'll then talk a little bit about how global warming has been reported in the media over the last 10 years or so, the role of the media, the role of scientists, and importantly the peer review process, which is the process by which scientific information is submitted to scientific journals. It's tested, some are rejected, some are accepted, and that goes on to inform the basis of our knowledge. I'll say a bit about who the skeptics are in terms of global warming, some frequently asked questions. I'll then go into a bit more about the science, because I know you're curious about what the actual science is telling us, but I won't go into a lot of detail about that. Some of those queries can be answered in question time. So I'll talk about the greenhouse effect, the evidence for climate change, causes of climate change, and finally a little bit about climate change projections and risk management. So firstly, I thought I'd do a bit of background on what the Australian Skeptics website has to say. And I noticed, without going through all of the detail here, that the word evidence pops up a number of times. And I'm really pleased to see this, because this is essentially what you have to base your views upon. It's not based upon assumptions or based upon hand-waving theories. It's actually based upon data and evidence. And finally, at the bottom there, I note that the website says that you're skeptical from everything from abracadabra through to zombies. And in the middle there is global warming. And that's why I'm here to talk today. So firstly, some words about the scientific method. As I mentioned, it is evidence-based. It encourages debate, and it tries to disprove new theories. And as I mentioned, skepticism is a healthy part of developing our scientific knowledge. Now, when these new theories can withstand critical testing, those theories become generally accepted. They become the paradigm. Now, the quality of science is controlled by this peer review process, and I'll say a lot more about that later. That is a process required for publication of research in reputable scientific journals. Now, some of these journal articles are actually quite controversial. It doesn't mean that they actually sail through and no one ever challenges them. There are a number of very good examples, particularly within climate change science, where some of the articles published in journals like Nature or Science have been challenged, and there's been quite a bit of debate, and that's very healthy. And of course, some things are known with greater confidence than others, and this is a really important point. So in the context of climate change, this is a little diagram which is on the vertical showing confidence level ranging from low to high, and on the horizontal, complexity ranging from simple to very complex. And up the top, where things are fairly simple and known with very high confidence, we have the fact that greenhouse gases keep the planet warm. Without greenhouse gases, the planet would be about 33 degrees colder than it is now, and life as we know it would not exist. Then as we move slightly further down in our confidence level, we know that the Earth has warmed by about 0.7 degrees Celsius since 1900, and there's been a rise in sea level. Moving slightly further down, most of the warming of the last 50 years is due to human activities that have increased greenhouse gases. And then off to the side there with a little bit more complexity, which is because this involves the use of computer models of the climate system, future greenhouse gas scenarios will lead to a warming of between about 1.5 and almost 6 degrees Celsius by the end of this century, and a sea level rise of between, that should be 9 and 88 centimetres by the year 2100. Again, a few more of these boxes you can probably read for yourself. One of, I guess, the most contentious issues is how much human activities have contributed to other changes in the climate system, such as the ocean temperature, the hemispheric contrast in temperatures, and in particular, regional warming. And I do want to emphasise one of these boxes down toward the bottom here, which is whether human activities have actually contributed to changes in regional rainfall and drought. This is something you'll hear a lot of conflicting views about. And in fact, there's not a lot of evidence at this stage to underpin the conclusion that there has been a human influence on changes in rainfall and drought. Different people will say that they've got more confidence in that, but the scientific literature doesn't support much on that. And then just finally, without reading through all of these, down the bottom right-hand corner, we've got that there's fairly low confidence and fairly high complexity in the issue of rapid melting of Greenland and the Antarctic ice sheets, which in turn would lead to very high rates of sea level rise and possibly a slowdown in the ocean's overturning circulation. So I think it's really important to, as a scientist, be explicit about the things that we know well and the things that we don't know so well.
A question on your chart. You said sea level's risen 18 centimetres since 1900.
Correct.
What's the evidence that? Where did that happen?
That's happened globally.
18 centimetres.
Correct. Yep, the range of uncertainties, 18 centimetres plus or minus about 3 centimetres. There was work recently published by Dr. John Church on this issue. Now, as you know, there's been a lot of media attention that includes some of the views of the skeptics, and that's all very well. It's great to see the debate being held in the public forum. But I've got to question whether this is very balanced. Now, of course, from my point of view, looking at the evidence in peer-reviewed scientific journals, global warming does represent a significant risk, and this is based upon the balance of evidence in some thousands of peer-reviewed journal papers. So in terms of, there's a very large quantity of evidence out there, and the quality is also very high because it's in these peer-reviewed journals. However, in the media, the views of a handful of skeptics are being included to provide a bit of balance. So you've got the scientists on one hand saying that global warming's serious, and you've got a handful of skeptics on the other side saying that it's actually not so serious. And so you've actually got to look at whether the views of some thousands of scientists are appropriately weighed against the views of a handful of skeptics. And as has been stated by this work by Boykoff and Boykoff, balanced reporting has allowed a small group of global warming skeptics to have their views amplified. And this has implied that there's little agreement about the basic facts of global warming. In addition, they go on to say that balanced reporting keeps a controversy boiling and perpetuates the public's perception that scientists are in disarray, which is actually misleading in the case of global warming because there's quite a lot of consensus. Consensus is not 100% agreement. There will always be differing views. But it's actually very misleading to say that the skeptical views are outweighing the views of some thousands of scientists who've published their work in the peer-reviewed literature. I'll say more about this. So the role of the media. I actually feel that the editors and journalists in the media have a duty of care to ensure that the facts are presented in context. They should seek information about the breadth of consensus or debate on an issue. And some parts of the global warming issue are very contentious. Other parts are actually well understood. They should question the credibility of particular scientists to quote outside their areas of expertise. And a scientist's credentials can be very easily determined. They should check whether statements being made by scientists can be supported by peer-reviewed publications, not by web documents and not just simply by opinion pieces submitted to newspapers. Now, the role of scientists like myself, we have to stick to our areas of expertise. I was actually interviewed on Four Corners perhaps earlier this year. Some of you may remember. It was about the role of scientists within CSIRO being gagged. I was actually trapped into this interview because I was talking a lot off camera about the impacts of climate change following a conference presentation. And the journalist caught me up with a question which was what I viewed to be a bit political, and that was, what should Pacific nations do about environmental refugees due to sea level rise? And I just thought, well, that's actually outside my area of expertise. So the way I answered that was to say, I can't answer that question. And for most journalists, when you say no comment or I can't answer that, they move on. But unbeknownst to me, this was a show about gagging of scientists. So she pursued with the same question in different ways. And I kept saying, I can't comment. That was misinterpreted as me being gagged. And in fact, what I was actually trying to say was, I can't talk about that because it's outside my area of expertise. So I'm really quite rigorous about that. As I've mentioned in that schematic diagram before, we should try and distinguish between what we know well and what we don't know so well. Be very explicit about the uncertainties. I'll mention a bit later about the Intergovernmental Panel on Climate Change, which is a body that assesses the breadth of knowledge. They have a whole chapter, one of their 12 chapters, just devoted to uncertainties. We have to acknowledge that there are issues over which there is significant debate. We have to publish in reputable, peer-reviewed scientific journals and ensure that even our consultancy reports, which are not journal articles, also undergo some very high level of peer review before publication. I keep talking about the peer review process, and I really think it's one of the main points I want to drive home to you today. It's a thing that underpins quality control in our science. So only the highest quality scientific journals have a rigorous peer review process, and they often have the highest rejection rates of the manuscripts as well. They're evaluated using various impact factors, which are based on how often these papers are cited in other journals. And there's a Web of Science which actually lists 8,500 of the most prestigious high-impact journals in the world. Now, the editors of the Web of Science each year look at an additional 3,000-odd print and electronic publications. They're systematically reviewed, but only about 10% of those are actually included in the next round of the highest quality journals. So it's a very rigorous process. Of course, scientists, as I mentioned before, should be aiming to have their work published in these peer-reviewed journals. And I think it would also help the public if we were able to educate them about the peer review process, because I think the public gets most of their information from the media, and they're not easily able to distinguish between what's a hand-waving argument and what's something that's very strongly based on peer-reviewed science. And just as an example, this is a bar chart showing over time, from 1992 to the present, the number of publications about global warming and risk management, or global warming and risk assessment. And it just gives you an indication of the fact that there's been a growing volume of knowledge on this particular topic. Just finally, I mentioned the Intergovernmental Panel on Climate Change, the IPCC. They do an assessment of the peer-reviewed literature on climate change every 5 or 6 years. And the last assessment was in 2001. They're currently working on the assessment for next year, which will be released around Feb. So there are 3 working groups. The first focuses on the underpinning science, much of which is debated by the skeptics. And in this working group, there are some 1,000-odd scientists and reviewers involved. These are all climate scientists. They are experts in their field. There's also a volume on impacts and adaptation, and almost 900 scientists and reviewers are involved in that. And mitigation, or reducing net greenhouse gas emissions, involves some 550-odd scientists and reviewers. So it's a very wide-ranging assessment. And the conclusions of the IPCC's assessment back in 2001 have been endorsed by the scientific academies of the G8 nations, plus Brazil, China, and India. So who are the skeptics? Getting back to, I guess, the issues that perhaps you're more interested in. There are apparently 3 different types of skeptics. Firstly, there are trend skeptics who deny that there is any global warming, who deny that there is this warming trend, who contend that some of those measurements are actually biased, that in fact they may be biased by warming in urban areas, which may not be related to greenhouse gases, might be more related to the increase in population growth. I can say they're a very small number now, because it's very clear that the temperature records that are used to calculate these trends are not taken from urban areas. They tend to be taken from rural areas where there's not a lot of population growth. The bigger group of skeptics really is the attribution skeptics, who accept that there's a global warming trend, but only see natural causes for it. So it's just natural variability. And this is a really active area of debate at the moment. And I'll say a little bit more about that later. Then finally, there are the impact skeptics who think that global warming is mostly harmless or even potentially beneficial. David Bellamy was one of these. He effectively said that high levels of CO2 actually have a beneficial effect for plants. They increase photosynthesis and they reduce plant water usage. So in the absence of anything else, it's really good news. Unfortunately, there are other things that go on when you increase CO2, A couple of those are increases in temperature and changes in rainfall. So it's actually not that simple. And then finally, there are those skeptics who are called contrarians or deniers, who have very fixed positions, and they're not as open-minded as I think you people are. Being a skeptic is about being open-minded. And some of those people with fixed positions have vested interests. So who are some of the overseas skeptics? I won't go through these in detail. There are a number of different institutes in the US. There's the Global Climate Coalition, which was actually disbanded about 4 years ago after the withdrawal of some of the big oil companies and motor manufacturers. There's this International Policy Network in London, a group in the EU. There's, of course, Bjorn Lomborg, who many of you will know, who wrote a book called The Skeptical Environmentalist a few years ago, one chapter of which was devoted to global warming. Of course, there's Michael Crichton, who wrote what he called a book of fiction about the state of fear, all about global warming and about greenies who are essentially trying to bring down the planet. There was a raft of different references at the end of that book, which made it actually seem more like a scientific assessment than a work of fiction. And then there are a few climate scientists who are actually genuine skeptics. Their expertise is in this area. Richard Linson and Patrick Michaels from the US are key people there. They actually publish their work in scientific journals, which is to their credit. That's where the debate should be going on, not so much in the media. And of course, that there are allegations that some of the skeptics are paid by the coal and oil industry, and there's a website there that lists a few of those people. And more recently, I think only about a month ago, the Royal Society in London noted that ExxonMobil has been giving support to a number of organisations that have been misinforming the public about climate change. So moving down to the Australian situation, I'm not afraid to name names. These people will be quite happy for me to mention them here, I think. Ray Evans, who's a member of the Lavoisier group, has written a little note about 9 lies about global warming, typical things that tend to be contentious. We've got Bob Carter and Ian Plimer, who are geologists. They've written a report that's on the IPA's website, the Institute for Public Affairs, and they've also written a number of newspaper articles. Bill Kinnamonth is a climate scientist. He used to work at the Bureau of Meteorology. He's written a book on climate change and natural hazard, and he's also come down to CSIRO and had a chat to us once or twice, and he's written a number of different media articles, particularly in the last week or two. We've also got Ian Castles, who was formerly the chief statistician, and David Henderson, who's an economist. They've been criticising the IPCC for the economic assumptions that underpin their greenhouse gas emission projections into the future. And there's a number of different journalists who you probably know quite well. So some of the tactics that the skeptics use, I guess excluding those that climate scientists like Richard Linson and so on who publish in the peer-reviewed literature, they tend to cherry-pick a lot of statistics that fit their fixed position. They rarely attend any of the science conferences that I'm at about global warming because I think they fear that they may be challenged. We're quite happy to talk to them, and we invite them down, as we have with Bill Kinnamonth and Ian Castles. Come and talk to us. We can help clarify any issues that might be contentious. Unfortunately, they rarely submit a lot of their manuscripts to peer-reviewed scientific journals where their theories and data will be rigorously tested. They do tend to publish papers, though, but they tend to be in skeptic-friendly journals that have a weaker peer review process. They write lots of things in the media. They write lots of things for web-based reports and in books. And they tend to regurgitate a lot of arguments that have been well and truly dealt with in the past. We keep finding the same issues coming up over and over again. And there's a tendency for some of them to comment on issues outside their area of expertise. And in response to this, I guess from a climate scientist point of view, I get lots and lots of queries about this week in, week out. It's actually helpful for us to document some of the contentious issues and respond in ways that are, I guess, scientifically rigorous. So, for example, the Environment Canada website has addressed about 48 frequently asked questions on their website. And both CSIRO and the Bureau of Meteorology have addressed 21 frequently asked questions and 12 hot topics on a couple of websites that are hosted by the Australian Greenhouse Office. So some of the hot topics that we addressed were, for example, how reliable are climate models? This is an issue that often comes up. It's one that's challenged by Bill Kinnamonth. The IPCC climate change scenarios, this is the issue that's been challenged by Ian Castles and David Henderson. How unusual is the late 20th century warming? This is getting back to the so-called hockey stick record of temperature, which shows over the last 2,000 years a fairly steady record of temperature and then a rapid increase in the late 20th century, looking like a hockey stick. And there's some contention about that. Is there inconsistency between the satellite records of warming in the lower atmosphere and the surface measurements? This was because there, at least until about 5 years ago, appeared to be, from the satellite records, no warming at the surface, and yet the thermometers at the surface were giving us a warming, and there was a discrepancy. That's since been resolved, and in fact there were corrections that needed to be made to the satellite data, which now have been made, and you still see the warming at the surface. Is the recent warming unusual in a geological context? So going back over now hundreds of thousands of years, where we know that there's lots of variability, and I'll say more about that later. Is the warming due to solar variability? Could global warming affect the thermal halide circulation, which is the overturning circulation of the ocean? What are the trends in extreme weather events, both locally and globally? Could the rainfall declines that have been occurring in southern and eastern Australia be due to changes in greenhouse gases, just natural climate variability, or perhaps even the ozone hole? Have methane levels stabilised? They have stabilised in the last 4 years, and there are different reasons for that. What might be some of the impacts in terms of species extinctions and abrupt climate change, fact or fiction? This was based upon The Day After Tomorrow, the film that came out about 2 years ago, which led to a lot of speculation that we may actually go into an ice age. So some science, some of the facts based upon very well-known information. Firstly, the greenhouse effect is a natural phenomenon, keeps the planet warm and livable. The main greenhouse gases are water vapour, carbon dioxide, methane, nitrous oxide and ozone, and also the CFCs that used to be in our spray cans. We know from measurements in both ice cores and from temperature records and measurements of gases that we make in CSIRO that over the past 200 years there's been an increase in greenhouse gas concentrations, about a 35% increase in CO2, about a 150% increase in methane. And basic physics shows that an enhancement of the greenhouse effect should lead to global warming. There's a very, very simple calculation that shows that without any other feedbacks, a doubling of carbon dioxide should lead to a 1.2 degree warming. The reason why we use very complex computer models of the climate system is because we need to know about the other feedbacks, the changes that might happen due to changes in cloud cover, changes in the ocean circulation, changes in vegetation. Would they offset that initial warming or would they enhance it? And of course, this whole issue has emerged really since the 1980s, and it's prompted a lot of analysis of historical records of the ocean, atmosphere, ice, and the biosphere. I like to show this diagram because it goes back 440,000 years. This sets the geological context. So what we have here is, I guess, time going back from the right to the left to years before present, and global average temperature on the vertical axis. I draw your attention to, firstly, the red line, which is records of temperature taken from little bubbles of air trapped in ice in Antarctica and Greenland. Where we get to a low point, that's an ice age. We've had about 4 ice ages in the last 400,000 years. They tend to occur every 100,000 years or so. And this is a well-known phenomenon because of so-called Milankovitch forcing. These are wobbles in the Earth's orbit that occur every 100,000 years, 40,000 years, and 20,000 years. The dominant cycle at the moment being 100,000 years. Now, actually, we know that without greenhouse gases, the amount of difference between an ice age and an interglacial period would be much less than the 10 degrees that you see here between the peaks and troughs. We've actually found out that greenhouse gases, in responding to this initial kick from the orbital variations, enhance the warming or the cooling response by about 50%. And so what we see is, in the green curve, the carbon dioxide concentration over the last 400,000 years, and it's pretty much in lockstep with the temperature. It is lagged behind the temperature change. So the orbital variations trigger a change in temperature, the temperature change triggers a change in the greenhouse gas concentrations, and then finally there's a response from some of the ice sheets. The interesting thing in this particular graph is what's been happening in the last 200 years or so, since the Industrial Revolution. Carbon dioxide concentrations are now up at 380 parts per million, whereas in the past, the natural variation was essentially between about 180 parts per million and about 280 parts per million. So we're now outside the natural range of variability. So this CO2 level is unprecedented. And as I've mentioned before, climate's always been variable. We've seen these variations from between ice ages and interglacial periods, and this will of course continue in the future. We will probably go into an ice age in 20 to 50,000 years. But the main point is what's going to happen in the next 100 years. And we think that the main driver of that climate variability will be greenhouse gases. Zooming in on the last 1,000 years, you get a little bit more detail here. We see, again, this is temperature on the vertical axis and time going back 1,000 years. The red curve is the temperature as determined. This is just for the northern hemisphere now. This is the so-called hockey stick graph, which was very contentious. In the blue, we see the measurements of carbon dioxide and the increase rapidly after the Industrial Revolution in the last 200 years or so. Now, there's been, of course, a challenge from a couple of people regarding the reliability of this temperature record. They say that there are much larger variations in the past, which mean that this warming in the most recent period of 100 years or so is not that unusual. Well, let's actually look at what has been found. This is now looking at not just one reconstruction of temperature over the last 1,000 years, but 8 different reconstructions independently put together. And so what we see here again is temperature on the vertical axis and time going backwards. The black curve here is the observed temperature record from thermometer measurements. And we can see that within the last 30 to 50 years or so, it is highly unusual compared to all of these other different records. And it is on the basis of this that we say the recent warming is unlikely to be due to natural variability. So I've talked a bit about very long-term changes. What's the evidence for climate change in the recent past, the last 100 years or so? We've seen a surface warming of about 0.7 degrees. 12 of the warmest years on record have occurred since 1990, the warmest being 2005, the warmest being 1998, second warmest being 1995, third warmest 2005, third warmest being 2004, and so on. Not only has there been a warming of the surface, there's been a warming of the upper ocean, a warming of the lower atmosphere, an increase in extremely high temperatures and a decrease in extremely low temperatures and frosts. Globally average, there's been an increase in precipitation, and this is what you might expect with a warming planet, where you get a warmer surface, more evaporation, more moisture in the atmosphere, and therefore more rainfall. But it's not globally uniform. There's been an increase in the intensity of rainfall and in tropical cyclones in a number of places. Sea level in the last 50 years has risen 9 centimetres. The oceans are becoming more acidic because higher levels of CO2 are being absorbed into the ocean. We've seen a reduction in snow cover and sea ice, and we've seen shifts in plants and animals that are consistent with global warming. So what are the causes of climate change? This is the really highly debated issue. And we know quite well from science that over the last 250 years, so since 1750, there are different elements that have been affecting the radiation balance of the planet, and this effectively is what leads to the equilibrium temperature at the surface. We know that, well, firstly, just to orient you with this graph, there are different amounts of either warming above the zero line, cooling below the zero line. The units here are in watts per square metre. It's a measure of radiation. The greenhouse gases of CO2, carbon dioxide, CH4, which is methane, N2O, which is nitrous oxide, and the halocarbons like CFCs, all represent an increase of the order of about 2.5 watts per square metre since 1750. Tropospheric ozone, which is ozone in the lower atmosphere, also has a warming effect. The depletion of ozone in the stratosphere has a cooling effect. Then there's a group of aerosols, little fine particles in the atmosphere, and also clouds that have differing amounts of radiative forcing, as we call it. Some have a cooling effect, like these sulfate aerosols, a very local effect, particularly in polluted areas of the world, and a relatively short-term cooling effect. They tend to get washed out by rainfall, for example. And some of these factors also have a warming effect, such as black carbon from burning of coal. A lot of uncertainty about this so-called indirect aerosol effect. This is the effect that aerosols have on the brightness of clouds and the lifetime of clouds. And a lot of people have also talked about solar variability. It has a slight warming effect, but it's relatively minor. So what's been concluded is that there are effects due to natural variability. I mentioned the wobbles in the Earth's orbit. There are also the 11-year sunspot cycle, volcanic eruptions, and the El Niño Southern Oscillation, which tend to give us droughts and very hot conditions. We also know that there are human activities that affect the planet, increases in greenhouse gases, changes in aerosols, ozone depletion, and of course land clearing. And I've mentioned before, most of the global warming since 1950 appears to be due to human activities. I won't mention the dot point down below. That's just a lot of other evidence for human activities affecting the planet. Am I getting a wind-up?
You have 9 minutes.
No worries. Sure, we'll get there. This is a diagram just showing how we attribute different causes to what's been observed in terms of global average temperature change. The red curve here are the observed global average temperatures over the last 150 years or so. And we can run global climate models just with natural factors alone, just with variations in volcanic eruptions and with solar variability. And you get a reasonably good match for the first part of this record up to about 1950, 1970 or so. But then they can't reproduce the observed warming in the last 30 to 50 years. When we run the same models just with human or anthropogenic forcing factors, such as greenhouse gases, aerosols, and ozone depletion, we get a reasonably good match in the first half of the period, not so good around the middle part up to about 1950, but then a very good match in the last 30 to 50 years. And it's not until you put both of these factors together, both natural and human factors, that you get a reasonably good match to what's been observed. And so the conclusion, based upon about 30 different papers now, is that most of the warming in recent decades is due to human activities. It cannot be explained solely by natural variability. So now we move into a bit of crystal ball gazing. Climate change projections. We don't simply extrapolate what's happened in the past into the future. It would be far too simplistic. What we use is very complex computer models of the climate system, which incorporate the basic physics and dynamics. And we drive these computer models by scenarios of changes in greenhouse gases, changes in aerosol emissions, and ozone depletion, the factors that we know a bit about. Now, we make a number of different assumptions about these emissions based upon how we think population may change, the rich and poor, economic growth, and technological change. And what's been finished up with is some, in fact, 40 different plausible emission pathways, 6 of which are shown here. These are carbon dioxide emissions in gigatons of carbon per year over the 21st century. And we see there's a wide range of uncertainty. This green curve here is one in which we assume a relatively low rate of population growth and a shift toward more renewable energy sources. Whereas in contrast, the dotted red line up here is a much higher rate of population growth and a strong dependence on fossil fuels in the future. All of these are considered plausible, but not necessarily equally plausible. No probabilities were put on these, unfortunately. And the issue that Ian Castles and David Henderson have is that they feel that this worst case scenario is unrealistic. When we run those emission projections through what's called a global carbon cycle model, which incorporates the fact that carbon dioxide, for example, has a lifetime in the atmosphere of about 100 years. Half of the emissions that are produced stay in the atmosphere, 25% go into the ocean, about 25% goes into the biosphere. So the net concentration of CO2 in the atmosphere is shown here. And despite the fact that even with the green emission curve going down, the concentrations still go up because CO2 has such a long lifetime in the atmosphere. So we're looking at concentrations by the end of the century of between about 550 and about 950 parts per million, bearing in mind that we're now at 380 parts per million. So much higher than future, much higher than the present. When we then run these projections of concentrations of greenhouse gases through climate models, we get an estimate of how temperature and sea level, for example, may change. And so we finish up with a global warming of between 0.5 and about 1 degree Celsius by 2030, increasing to between 1.2 and almost 4 degrees by 2070. And the sea level rise up to 17 centimetres by 2030, up to almost 0.5 metre by 2070. But again, with a range of uncertainty based upon 2 things. Firstly is the uncertainty in those emission projections that I showed on the previous slide. The second thing is uncertainty that comes from the global climate models, so I guess scientific uncertainty versus behavioural uncertainty. So how well are these IPCC projections doing against our observations? The solid blue curve here are the observations of carbon dioxide concentration since 1970, and the dotted lines in the second half of the graph are those projections from 1990. And we can see that at least in terms of carbon dioxide, we're tracking along the highest emission pathway. And so this is something that I guess Ian Castles and David Henderson had not expected. It may not last. There are fluctuations from year to year and from decade to decade, but it's an interesting result. What about temperature? Again, in this diagram from 1970, the solid red and blue curves, which are based upon two different records of global average temperature, seem to be tracking toward the high end of the range that was predicted from 1990. And likewise for sea level. Again, we're tracking toward the worst case scenario rather than the lower estimates. So that's interesting. On the basis of the fact that I don't have time, and we do have a bit of time for questions, I'm not going to say anything about the impacts of climate change. I have some slides that I have in reserve that I can use, but I really just wanted to get to the generic issue of risk management, because this is really what global warming is all about. It's about making decisions even though there are large uncertainties in some aspects. So risk management is I guess, in terms of climate change, twofold. We can manage the risk by reducing greenhouse gas emissions, and we've heard a lot about that. We've heard about the Kyoto Protocol. We've heard about new Kyoto, which is apparently going to get us to much deeper cuts in emissions in order to slow the rate of global warming and therefore avoid some of the worst impacts of climate change. And this diagram is essentially showing the global average temperature on the vertical versus time across the horizontal. The range of uncertainty being that which I showed on a previous slide. So by the year 2100, we have a warming of about 1.5 to almost 6 degrees Celsius. So the bubble on the top there is showing risk management through reducing greenhouse gas emissions. That reduces the higher rates of global warming, but it has a delayed effect. So you don't see the benefits of that for some decades to come because these greenhouse gases have such a long lifetime in the atmosphere. The second way to manage the risk is to adapt, to accept that there is going to be some inevitable amount of warming that we have to adapt to, that we can't avoid. And risk management through adaptation actually helps to deal with the low rates of global warming, and it's immediate. It gives you an immediate benefit because you deal not only with future climate change, but you deal with current variability and extreme events. So there's a real synergy between both managing the risk through reducing emissions and through adapting. And I guess we're seeing examples of adaptation right now through all of the changes in water policy that we're seeing, whether it be recycling or desalination or building another dam. These are the things that are being considered now. Now, adaptation, of course, is a dynamic process. We start with developing information in terms of knowledge, data, and tools. We then use that data in risk assessments. It's a lot of the sort of work that we do in terms of assessing impacts on, say, coastal flood risk. And recently, the Australian Greenhouse Office released a guide on risk management for climate change. Then, ideally, we want to get to the situation where we can mainstream climate change in adaptation policy. So it's incorporated into plans as part of a standard procedure. And having done that, we then, of course, need to go through a loop where we evaluate how well we're doing and we monitor how well we're doing. And finally, of course, at the same time, we're raising awareness and building capacity. And all of this goes into eventually implementing adaptive strategies. And, of course, there are barriers on the way. There are institutional barriers, there are technological barriers, and there are cost barriers. So it's a real challenge. And doing this isn't something that you just take off the shelf and you foist upon people. It has to be done in a participatory way. It has to involve the community, government, industry, scientists, and others at most stages of the process. A quick word on reducing greenhouse gas emissions. One of the things that's driving this is Article 2 of the United Nations Framework Convention on Climate Change, which was signed back in 1992. This article says that we should avoid dangerous climate impacts. Now, dangerous is a very emotive word, and it's not very well defined. Science can contribute to this, but there are a lot of other socio-political aspects as well. In terms of the scientific aspects, a lot of the impact assessments indicate that, for example, for a 1 degree global warming, we would expect annual bleaching of coral reefs. For a 1 to 2 degree warming, millions of more people are at risk of food and water shortage and a greater acidification of the oceans. For a 2 to 3 degree global warming, perhaps irreversible melting of Greenland, which would, over some hundreds of years, lead to a 7-metre sea level rise. For a 2 to 4 degree global warming, breakup of the West Antarctic ice sheet, which over thousands of years would lead to a 4 to 6 metre sea level rise, and for a 3 to 4 degree global warming, perhaps a slowdown in this ocean's overturning circulation. So the question is, at what level should we stabilise greenhouse gas concentrations to avoid dangerous climate change? Out of all of these different thresholds, which would you choose as being dangerous? It's very subjective. Now, some of the EU governments and even some of the state governments now are suggesting we should avoid a 2 degree warming. To do that, using our global carbon cycle models and working backwards, we would need to stabilise carbon dioxide concentrations at 450 parts per million. That gives us a warming of 1.2 to 2.3 degrees Celsius. Now, that concentration in turn requires that emissions are cut by about 40% globally by the year 2050 and 70% by the year 2100. You may all be hearing that the 60% figure being bandied about for the year 2050. This is recognising that developed countries and developing countries have different pathways, and it's likely that developing countries will continue to increase emissions much more rapidly than the developed countries. And so the developed countries are talking about a 60% reduction to compensate for that. So finally, my last slide. I hope I've convinced you that climate change is real and it's underway, that most of the warming of the last 50 years is due to human activities that have increased greenhouse gases. Climate change will continue into the 21st century because we know greenhouse gases are likely to continue to increase. Significant impacts are likely, and risk management requires both adaptation and emission reductions. Thank you.
Excellent talk, factual, scientific, level-headed. First point, you've used the term climate change skeptics. Most people do. I'd like to ask that all of us here don't use that term. It demeans the people here and the organisation. Let's insist on using the term climate change denier for everything.
I take your point, and I've read a bit of literature about this, and I tried to make, I guess, a distinction between the skeptics who I think are open-minded. They're looking for evidence, and that's great. It's a part of the scientific method. And those that have the fixed positions who are a bit closed-minded, who are the deniers and the contrarians.
But in the public, we should use deniers. The second point is you've focused on CO2. In New Scientist, they've been publishing articles that if the tundra in the northern regions, the Arctic, melts, it will release stupendous amounts of methane, which is much more powerful than CO2. And that is one of the tipping points we should be focusing on, not the change in the Atlantic Gulf streams. What's your view?
That's very true. Methane has, in the last 4 years or so, actually stabilised, and the theory there is that this is a response to efforts particularly in Russia to cap off some of the leaks from their pipelines. But we think it may just be a lull, and indeed that there is a bigger risk of increasing methane emissions from the tundra. Also the possibility of release of methane hydrates, which are trapped down in the ocean, that with a warmer ocean may actually become released. And in fact, I believe that a couple of the extinctions have been linked to release of methane hydrates. It's a very large amount of methane there. Indeed, this is a very important issue. And in addition to that, more recent work has indicated that feedback from the biosphere, which has not been incorporated in the projections that I've shown, may actually lead to a greater increase in carbon dioxide release. So there's a number of, I guess, natural indirect effects on both carbon dioxide and methane that have not been incorporated in these projections that do need to be incorporated.
The thing that I have read about what's happening in northern Russia is that the amount of methane being measured this year by Russian scientists, and for the first time have made a consistent attempt at measuring it across the north, is at least 50 times higher than their previous believed emission rates, and they stated categorically, therefore at present methane emissions from North Russia are a greater contributor to global warming than all other gas emissions combined on Earth. Now they're quite categoric about that. It was referred to in New Science in the last couple of weeks.
That's interesting. I've not read that yet. I'd be interested to see if it gets into one of the more reputable peer-reviewed journals. Yeah, it could quite well be true.
I find your sawtooth correlations very persuasive. Could you comment on what is the fact, or what are the factors that bring the curve down? Can we learn from them?
Okay, so we're talking about the changes in temperature and carbon dioxide over the last 420,000 years.
On the 10,000 plus year timescale.
Yeah, so I guess, so you're pointing out that I guess from an ice age we then fairly rapidly go up the sawtooth to an interglacial period, a warm period, which we're currently in. So what's driving the decline? It is the change in the orbital parameters of the Earth. There's 3 different orbital parameters. Can't really see how we can change them quickly. Yeah, sorry?
Is it solely due to that?
Yes, it is combined. Yeah, so the main driver is the change in the orbital, the wobbles in the Earth's orbit, reinforced by a response from both greenhouse gases and the ice sheets. So it seems that when we go into a cold phase, there's less radiation from the sun because of a wobble. That then leads to less emission of methane from tundra because the tundra starts to get frozen, less release of carbon dioxide from the oceans and from the biosphere, and then that in turn leads to a slight cooling, which in turn triggers a greater growth of sea ice and a build-up of polar ice, and you know, before you know it, you're into an ice age.
There was at least one major depression. Any known cause for that?
At what period?
Halfway along that curve you showed, there's quite a dip after one of the warm periods. A very sharp dip, nothing astronomical.
Yes, I mean, they're actually beyond those 100,000, 40,000 and 20,000 year cycles, a number of smaller cycles, which in fact led to what was called the Little Ice Age a few centuries ago. So there are other cyclic factors which I think are responsible for some of those.
We all pray for another Little Ice Age.
That's right, it's exactly right.
Last question in front of you. You didn't explain where the data came from the 400,000 years ago.
That's from little bubbles of air trapped in Antarctic ice and from Greenland.
Is that the only source?
Yeah, essentially. There's also a bit of information from tree rings and from coral cores, from lake sediments. These are so-called proxy data, but most of that evidence that I showed is from ice cores.
Join me again. Thank you.
Thank you.